Good morning, everyone. This is a short presentation of SARAS Sarlux Refinery and the SARAS Group. SARAS is an independent refinery company which basically has different branches. One branch is supply and trading, which exploit market opportunity for both crude and products, and is based in Geneva from 2016. We have also a refinery which is located in the south of Sardinia in Mediterranean and is the biggest refinery in Mediterranean area with a capacity of 300,000 barrels per day. Is a top tier refinery with a Nelson index of about 11.6, and the yield of light distillates is equal to 85%. Fuel oil yield is approximately 7%. We have also petrochemical integration from 2015. We have also the largest liquid gasification plant in the world with power with 565 megawatt of installed capacity. And basically it's a conversion of heavy refinery and into clean gas and electricity. We have also a market share, an important market share in Italy and also in Spain, and we have a storage capacity of about 4.3 million cubic meters. We have also renewable energy, wind energy, basically in Sardinia, with an electricity production of about 250 gigawatts per year. This is a simplified scheme of our refinery, which has 3 topping units, 2 vacuum FS breaker, and 1 FCC, 2 hydrotreater, a CCR, 2 reformers, and the power generation plant. This is a very simplified scheme, and as said before, this is the yield scheme, a simplified yield scheme. Which crudes we process? We process crude from all over the world, and basically from 2015 till now we process more than 40 crudes, very different from country of origin and for characteristics.
So thank you, Andrea, for the presentation of SARAS Group. I'm now briefly introduce Petroval Company. We are providing solutions worldwide for every refining and petrochemical industry. We have more than 30 years experience working in more than 50 countries in the world. We have most of the international safety certifications, and we employ only long experienced people with more than 30 specialists available around the world. We are specialized in 2 specific departments. Catalyst departments, dealing with all the loading and unloading process and technical support of fixed bed reactors. And then the energy department, that is my side, taking care of tube inserts for the heat exchangers and infrared tomography for the furnaces. We will talk today about tube inserts for heat exchangers. We have these kind of technologies that can provide significant improvements in terms of fouling mitigation, but also in terms of heat transfer improvements. And when we combine these 2 effects, we can typically provide significant energy savings that will be converted also into reduction in CO2 emissions. And we will see in details what we can reach. We have 3 technologies. The first one is called Fixotal. This one is a fixed device that is generating turbulence in the feed and that generates the renewing of the boundary layer at the tube wall. And by doing so, we have a significant effect on the fouling deposition, especially when it is related to wall temperature. And we also have a good impact in terms of heat transfer improvement because of this extra turbulence that we generate. We have then 2 technologies that have a mechanical cleaning effect. We have the turbotal on the left that is rotating inside the tubes. So this is combining a mechanical effect of brushing the tube walls with the increase on the turbulence. And then on the right side, we have the spiral that is fixed on both ends and is vibrating inside the tubes. So this is also generating some brushing inside the wall of the tubes and an increase on turbulence level. So all these three technologies, and we will see now applications on SARLUX refinery. We have 3 turbotal applications there, and we will present the results of these applications. What you see is a short video of the turbotal rotating. Depending on your internet stream, it may be slowed down, but you have to know that it is typically designed to rotate at about 1000 RPM during normal operation. I will present to you now the first case study. So we have 3 applications of 4 heat exchangers on the 2 topping units in SARAS refinery. So for each of these cases, we will show you the fouling factor evolution on the left. And below, we will show you the overall heat transfer performance, that is comparative runs that we will show to identify the benefits of these applications. So on this first train, we had 4 exchangers equipped, and we had a fouling rate divided by 2 on the first run. That's the black line with the red dots. So we see there was one recirculation during that period, but that did not affect, and it was the same inserts. And then we had a second run in 2020, during which the fouling rate was divided by 4. But that was also thanks to an upgrade on the design to also be able to comply with low period of performance. Typically, when the flow rate is reduced, we need to slightly modify the design to improve the performance. So if we compare the level of improvements in terms of heat transfer, at the start of the run, we were on the first run 20% higher, but on the second run, we were 60% higher, thanks to this new design. And when we look on the same period than the original reference run, that was about 200 days, we see that after 200 days, we are about 80% higher after the first run. And on the second run, we were about 180% higher than the reference run. And then when we went until the end of the first run with Turbotal, we identified that we were still 20% higher after 4 years, compared to the reference run after 200 days. So this shows very significant improvements that were linked to the Turbotal implementation, and also due to the upgrade of the design. And typically that has multiplied by 4 the run duration, even if there was run recirculation that was due to normal maintenance. On this particular application, we identified sometimes some limitation in terms of performance that was due to the residue temperature. And when it was around 190 to 200 degrees C, we saw some limitation in performance. And that was basically due to the fact that the second train of exchangers that was just downstream was performing very well, and that was also impacting the residue temperature. So we'll show you now about the second set of exchangers that is next downstream of the first one. And that's typically the same idea, except that during the first run, we identified that the fouling rate was reduced by only 20%. And we investigated to identify the consequences of that. And we found that typically the range of operation that was designed originally was not really fitting with the real operation. And that's why we redesigned it in 2018 to fit on the complete range of the flow during the normal run of operation. And we have here the comparison between the reference run and the gains that we can reach with the Turbotal applications. The first run and second run, we see typically a large gain in terms of energy recovery, 20,000, 30,000 gigacalories per year. And when we convert it to energy and to money, that represents more than €1 million. So that's really significant. And the side effect that is really important for us now in Europe and many other countries that are also impacted with CO2 taxes, it means that as we save energy, we reduce the consumption of fuels. And by doing so, we reduce the CO2 emissions. So the impact in terms of tax of CO2 emissions is also very interesting, 300, 400,000 kilo euros per year. So that was the first two applications we have on the first crude distillation unit. And we have also another application with the turbotal. It's again 4 exchangers applied on the hot train on this second CDU. We see as well the performances on these runs. We have highlighted the fouling rate was reduced by 33% on run 1 and 2, which was quite already interesting. And the gains on the U were in the range of 30 to 40% at the start of the run. We redesigned it as the bundle were replaced as identical with in November 2019. And we had then very stunning performances. We had the fouling rate was divided by 4, and the gain in U at start of the run was more than 90%. And typically this was due to the two effects, the new design of the turbotal, but also the new exchanger, even if they were in carbon steel still, there was no iron sulfur, and that was really impacting significantly the level of performance, as there was no fouling deposition at the beginning of the run. We evaluated the heat recovery during the reference run. That was only 6 months. And when we compared that to the turbotal in the first and second run, we had a large improvement. And during the last run we operated in 2019 with the new exchangers, with the new turbotal design, we reached a very high level of energy recovery. And typically the comparison between the reference run and the last run, we have more than 20,000 gigacalories of energy recovered, and that's just within 6 months. So that represents again about 1 million of energy recovery and CO2 emissions that have been avoided. So that's another case where we see with a retrofitting of tube inserts in this kind of exchangers, when we select the right exchangers, we can really provide very interesting improvements. And the paybacks are very short because of the amount of energy is recovered and the CO2 emissions are reduced. That makes very, very short paybacks. So to conclude, we will just highlight that in fact we have to redesign the inserts, and that was to fit with the real flow conditions, to comply with the range of crude density and viscosity we see from 0.84 to 0.92, and also to fit with the range of operation from 60 to 100% of the design capacity. And as we have reached, thanks to this COVID situation, we had many of the refineries have been forced to operate at very low flow rates, and that has an impact on the rotation speed of the inserts, of course. So that's why we need really to anticipate any low periods or any high periods to update the design and identify the best compromise to fit on the larger range of flow conditions.
Thank you, Nicolas. Just a short recap of the achievement we obtained in the Sarlux refinery. Basically, we had a fouling rate more than half than before. We had for sure more flexibility in operation, in the sense that we had less pressure drop increase in the heat exchanger train, and of course more heat transfer performance. We had a substantial energy recovery. In fact, the payback of this insert is just in a few months. And of course, we also use less fuel, and so a reduction in CO2 emission. We didn't install all the insert in one time, but we installed in 3 different situations the different inserts, and we are also inserting other inserts in other exchanger in other units.
Yeah. And as we know, this technology can easily be implemented during the cleaning shutdowns. The installation is very short and there is no hot work necessary for that. It can be retrofitted to existing exchangers, even though we can also do it from new designs. And this is really reliable. There is no breakage during normal operation and within the mechanical lifetime. As every mechanical pieces, there will be some erosion during the runs because of the mechanical cleaning effects, but it is perfectly controlled with no damage on the tube itself. So when we operate in normal operation within the normal range of flow conditions, there is clearly no risk for the operations. So I would like to thank SARAS for their application and for their sharing the presentations and all the parameters of the operation. We've made very good interaction together, and we have provided a huge improvement for that refinery, and we are very happy for that. We're sure there will be many other opportunities, and thank you again.
Thank you. Thank you to you, Nick.
Thank you.